Today we'll look at really a very important problem insofar as applications are concerned, and kind of surprisingly, as far as engineering applications are concerned. We'll say more about that a little later. But that's the scattering from a square well potential. We'll ultimately do both, but for right now, we'll be looking at an attractive square well. And I've got the potential for an attractive square well here. Uh, and I've drawn it down below. So it's attractive. We set it equal to zero. The potential is zero up from minus infinity to zero. It's minus V naught, where V naught is some positive number between x equals 0 and x equal to 2a, which I'm going to reduce as the width. That's the actual width. Remember, the radius of the well is a, and then so the diameter, in this case, the width of it is w, twice times the radius, and then 0 for x greater than w all the way to infinity. Uh, what I'll assume is that we are firing a particle in from infinity over here, and I don't want to look at the bound state problems now, so I want this energy to be greater than the greater than zero. And I assume that I know the mass and I know how much energy, the kinetic energy, I fired into this potential well with. Uh, and that's our incident wave, quantum mechanical wave that's incident on it. And then we want to look to see what happens and essentially solve this problem. In addition, I'm going to assume that I know what V naught is. That's the depth of the well, and V naught is a positive number, and I explicitly have the negative sign here. Well, the first thing is to get the a solution to the time-independent Schrodinger equation in each area. Since the potential is piecewise defined, we have to define a wave function piecewise and then match things up at the edges of the potential. But write down the time independent Schrodinger equation is here. But so long as x is less than 0, then uh, this potential term vanishes. And we've got the familiar equation. We've done this several times by now. And we bring the 2m h bar squared over to this side with the minus sign. Introduce this constant. Remember, E is constant. It's bigger than 0. All of this is known. And so it's some positive number that I could put in there if I wanted to do so. And then the equation to be solved for x less than 0 is this one. And again, we've done this multiple times as well. It's composed of a right-going wave, which is the incident wave. It has positive k. And it has a reflected wave. I'm going to call the amplitude of the reflected wave a sub r. And it's going in the minus x direction. For x between 0 and w, the time-independent Schrodinger equation up here becomes a little bit different, because now in this region the potential is minus V naught. So I substitute for V of x minus V naught, and I get this equation. And that one we've done similar things for as well. Take the V naught term over to the other side, and I can factor out the psi. And then multiply through by 2m h bar squared. And ultimately, I rearrange this equation into this form, where I've introduced k prime is 2m e plus v naught h bar squared. Remember, e is a positive known number, and v naught is also a positive known number. So again, in principle, I know everything here, and I can get this numerical value for k prime for a given instance. And that's in between. It's only good for x between 0 and w. And one can choose different arbitrary constants to just get the general solution. And I chose those to be b for the right-going wave and c for the left-going wave. And then finally, we need to look at x greater than w. And there, the time-independent Schrodinger equation, again, the potential vanishes in that region, and so we get exactly the same equation we got for x less than 0. And for it, I wrote the solution, the general solution, an amplitude a sub t. This is the transmitted part, it's going toward the right. And then I get another one, which I wrote, at least temporarily, as an amplitude f times e to the minus I kx. This one's going to the right. This one is going from to the left from the right. So our general solution, I probably could have just written this down immediately, is of this form in all these regions. And this sort of reiterates energy is bigger than 0, it's known energy and known V naught. And now that I'm going to assume, like we always do on these scattering problems, is that we're only firing particles in from the left side of the potential, from minus infinity going toward the right. This term here corresponds to particles being fired in from the right going toward the left, and that would be like scattering two beams simultaneously off of it. And by the setup of the usual experimental arrangement, then we're going to assume that we're not having any incident particles coming in from the right and moving to the left, so we'll set f equal to 0. So altogether, we've got something that looks like this. We've got an incident wave, a e to the I kx. We've got a reflected wave over in this region, ar e to the minus I kx. In between, we've got a right-going and a left-going wave, and I have a different k prime, and then I get a transmitted portion in general that has amplitude at and goes e to the I kx, and then the incoming wave over here we've set equal to 0. So graphically it looks something like this, and in terms of our solution, we have it in this form. The incident beam, the reflected, a right going and a left going in between the barriers, and then finally a transmitted portion. And the k's and k primes are constants that we know from a given situation in which we're providing. We know the energy E that we're firing it in, we know the mass, and we know the depth of the potential barrier. Well, we'll pick up here on the next installment of this multi-part lecture as we provide more details on the problem.